Subscribe to the channel so you don't miss out on any of these videos. Imagine standing on the surface of a distant planet, staring out into the vastness of space, where a faint breeze brushes against your skin. In our own universe, such a phenomenon doesn't merely exist on planets, it exists on a galactic scale. These winds are not gentle gusts of air that we experience here on Earth, but powerful, high-velocity flows of gas and dust. These cosmic winds, often referred to as galactic winds or superwinds, play a significant role in the evolution of galaxies and the universe as a whole. Driven by intense astronomical forces such as supernovae and the mysterious active galactic nuclei, AGN, these galactic winds are among the most fascinating yet poorly understood features of our cosmos. The very idea of a wind traveling through the vast emptiness of space may seem paradoxical, given the lack of air or medium for it to travel through. Yet, these galactic winds are real and can have profound impacts on the birth and death of stars, the evolution of galaxies, and the delicate balance of the intergalactic medium. For many astronomers, understanding galactic winds is a key piece of the puzzle in explaining the complex mechanics of galaxy formation and evolution. To truly appreciate the nature of these cosmic forces, it's crucial to first understand their origins. Galactic winds are typically powered by the energetic events within the heart of galaxies. Among these, supernovae and the active galactic nuclei AGN, the supermassive black holes located at the center of many galaxies, are the primary drivers. A supernova, a stellar explosion marking the death of a massive star, releases an immense amount of energy, propelling a shockwave of gas and dust into the surrounding space. Likewise, AGNs, which can outshine entire galaxies, emit powerful jets and radiation that can trigger vast outflows of material from the galaxy. Together, these forces can launch winds at speeds ranging from hundreds to thousands of kilometers per second, scattering gas and dust across vast distances. One of the most fascinating aspects of galactic winds is their role in distributing gas and dust throughout the galaxy. In the process of star formation, galaxies accumulate large quantities of gas and dust in their stellar nurseries. These materials are essential for the creation of new stars, planets, and even entire solar systems. However, galactic winds can play an opposing role. While they can inject fresh material into the intergalactic medium, they also remove valuable gas and dust from the galaxy. This process of gas expulsion can suppress or even halt star formation, which in turn affects the overall evolution of a galaxy. As a result, the balance between galactic wind production and star formation becomes a critical factor in determining a galaxy's future. The energy released during a supernova or by the active galactic nuclei can create powerful shockwaves. These shockwaves push gas and dust outward, often at speeds so high that they exceed the escape velocity of the galaxy itself. When this happens, the expelled gas is carried far beyond the galaxy's gravitational pull, effectively redistributing the material into the intergalactic medium. This process of material exchange can have far-reaching consequences, as the expelled gas and dust can later be incorporated into other galaxies or even contribute to the formation of new galaxies. Thus, these galactic winds, while destructive to the individual galaxy, play a critical role in the larger-scale dynamics of the universe. Understanding how galactic winds interact with the intergalactic medium is another crucial aspect of their study. The intergalactic medium, which consists primarily of hot, ionized gas that fills the space between galaxies, is influenced by the outflows of gas and dust from galaxies. When galactic winds expel material, they heat the intergalactic medium and can significantly alter its composition. The interaction between galactic winds and the intergalactic medium is an ongoing area of research, as scientists try to determine the full impact of these interactions on galaxy formation and the overall structure of the universe. The influence of galactic winds extends beyond the boundaries of the galaxy itself. In some cases, the energy from these winds can penetrate deep into the surrounding environment, heating the gas in the galaxy's outskirts and causing it to expand. This expansion can have significant effects on the galaxy's morphology and structure. In fact, some of the most massive galaxies in the universe, particularly those at the centers of galaxy clusters, are believed to be shaped in part by these energetic outflows. As gas and dust are driven out of the galaxy, the available material for star formation is depleted, leading to a slowing or cessation of new star births. This process is part of what is known as galactic feedback, a crucial mechanism in regulating the growth and evolution of galaxies. In addition to influencing star formation, galactic winds have a significant impact on the evolution of black holes. The supermassive black holes at the centers of many galaxies can exert immense gravitational forces, pulling in nearby gas and dust. As this material spirals toward the black hole, it heats up, emitting radiation that can generate powerful jets of matter. These jets, along with the intense radiation emitted by the active galactic nuclei, can drive galactic winds, expelling material from the galaxy and shaping its overall structure. The interplay between the central black hole, the surrounding galaxy, and the galactic winds is a fascinating area of study, as it provides valuable insights into the role of black holes in the broader context of galaxy evolution. It's also worth considering the impact of galactic winds on the larger-scale structure of the universe. While the influence of any single galactic wind may be localized to its parent galaxy, the collective impact of galactic winds across the cosmos can have profound effects on the distribution of matter in the universe. By ejecting gas and dust into the intergalactic medium, these winds contribute to the cosmic recycling process, which helps to redistribute the material that will eventually form new stars and galaxies. This process of recycling is an essential part of the universe's ongoing evolution, ensuring that the raw materials for new stars and galaxies continue to be replenished. The study of galactic winds also sheds light on the nature of cosmic evolution itself. In the early universe, galaxies were more compact and gas-rich, with rapid rates of star formation. Over time, as galaxies grew older and more evolved, the balance between star formation and gas expulsion shifted. Galaxies with intense supernova activity or powerful AGNs began to lose significant amounts of gas, slowing or even halting the formation of new stars. This transition from star-forming, gas-rich galaxies to more passive, gas-poor ones is a key feature of the cosmic evolution process and is heavily influenced by the dynamics of galactic winds. Moreover, the study of these winds also touches on some of the more speculative aspects of astrophysics, such as the potential for life beyond our own galaxy. If galactic winds can disperse key elements, such as carbon or oxygen, across the universe, these materials may eventually find their way into other regions, potentially contributing to the formation of life in distant galaxies. This idea adds an intriguing dimension to the study of galactic winds, as it connects the dynamics of galaxy formation with the possibility of life in the broader universe. As we look further into the future, the study of galactic winds could provide critical insights into the ultimate fate of galaxies, stars, and the universe as a whole. Understanding the mechanisms that drive these winds will help us to better understand the delicate balance of forces that shape our universe, from the birth of stars to the formation of galaxies and the potential for life beyond Earth. The interplay between supernovae, AGNs, and galactic winds is an essential piece of the puzzle, and as our observational technology continues to improve, we may one day have a clearer picture of how these cosmic phenomena influence the vast expanse of space. Despite all that we have learned about galactic winds, much remains to be understood. The precise mechanisms by which supernovae and AGNs drive such powerful outflows of gas and dust are still a subject of intense study. The influence of these winds on the evolution of galaxies and the intergalactic medium is far more complex than we initially imagined. But as our understanding deepens, we come ever closer to uncovering the full extent of their impact on the universe. As we continue to explore the intricacies of galactic winds, it's important to consider their role in the feedback loops that govern galactic evolution. These feedback loops are essential mechanisms by which galaxies regulate their own growth, star formation, and the distribution of matter. Feedback is a key concept in astrophysics, particularly when examining how galaxies evolve over time. The process involves an ongoing interaction between the galaxy's stars, black holes, gas, dust, and the broader intergalactic medium. In the case of galactic winds, feedback operates in two primary directions: outwards, as gas and dust are expelled into space, and inwards, as the energy released by supernovae or AGNs triggers further processes within the galaxy itself. When a supernova explosion occurs within a galaxy, it expels vast amounts of gas, enriching the surrounding space with heavier elements. This ejected material may later fall back onto the galaxy, feeding future generations of stars and adding complexity to the interstellar medium. Such a feedback mechanism can enhance or suppress star formation depending on how much gas remains in the galaxy. If the outflows are particularly powerful, they may deplete the gas reservoir, shutting down star formation. On the other hand, if only a portion of the gas is ejected, the remaining material can spark new stellar births. These complex interactions are at the heart of galactic evolution, where galaxies oscillate between periods of rapid star formation and relative quiescence. One key observation in the study of galactic winds is how they influence the chemical composition of the universe. The gases expelled from a galaxy during a galactic wind event are not empty. They are rich with the byproducts of stellar fusion. As stars go through their life cycles, they produce heavier elements such as carbon, oxygen, and iron. When these elements are expelled into the intergalactic medium via galactic winds, they contribute to the broader chemical makeup of the universe, which ultimately has profound consequences for the formation of future stars and even the potential for life elsewhere in the cosmos. In this way, galactic winds act as a form of cosmic recycling, repurposing elements across vast distances of space. While supernovae and AGNs are often the most prominent sources of galactic winds, other less understood factors also contribute to these outflows. For example, interactions between galaxies can trigger massive wind events. When galaxies collide or merge, the gravitational forces at play can cause significant disturbances in the gas and dust within them. These interactions can funnel gas towards the central black holes, fueling AGNs and sparking energetic outflows that drive galactic winds. Similarly, when smaller galaxies are accreted into larger ones, their gas is often swept up by the wind flows, further altering the dynamics of the parent galaxy. Moreover, the environment in which a galaxy resides also plays a crucial role in the development of galactic winds. Galaxies located in dense regions, such as galaxy clusters, experience a different type of wind than isolated galaxies. In these dense environments, the surrounding medium is often heated by the radiation and shock waves generated by galactic winds, creating a turbulent and energetic backdrop. The interplay between the hot, ionized gas in these regions and the wind-driven material can lead to the formation of large-scale structures such as the intercluster medium, which plays a key role in regulating galaxy formation within clusters. Despite the energy and scale of galactic winds, much about their precise nature remains a mystery. For example, the exact mechanisms by which AGNs produce the powerful outflows that drive these winds are not fully understood. The current leading hypothesis suggests that the energy radiated by the supermassive black holes at the centers of galaxies plays a significant role in powering the winds. These black holes can unleash jets of high-energy particles and radiation, which in turn heat the surrounding gas and drive it outward at extreme speeds. However, the detailed processes at work, including how the black hole's accretion disk interacts with its surroundings to produce these winds, are still a topic of active research. One particularly challenging aspect of studying galactic winds is the difficulty of observing them directly. Most of these winds occur in the farthest reaches of galaxies, often in regions that are obscured by dust and gas. Astronomers rely on indirect methods, such as the observation of emission lines from ionized gas or the detection of specific signatures in the X-ray and radio wavelengths, to infer the presence of galactic winds. As observational techniques continue to advance, however, we are beginning to develop a clearer picture of how these winds operate. Telescopes that can observe across multiple wavelengths, such as the James Webb Space Telescope and the upcoming Athena mission, will provide more detailed insights into the role of galactic winds in shaping the universe. The effects of galactic winds extend beyond the individual galaxy and can influence entire cosmic structures. For instance, the material expelled by galactic winds is often not contained within the galaxy itself but is injected into the intergalactic medium, a region of space that exists between galaxies. This material can mix with other expelled gases and contribute to the large-scale chemical enrichment of the universe. As these winds expand outward, they can also contribute to the cooling of the hot gas and galaxy clusters. This cooling process can prevent the formation of new stars within the clusters, as the loss of gas inhibits the creation of fresh stellar nurseries. In this way, galactic winds not only shape the evolution of individual galaxies, but also play a critical role in the larger-scale dynamics of the universe. As we delve deeper into the study of galactic winds, it becomes increasingly apparent that these phenomena are not merely a byproduct of stellar activity or black hole dynamics, but a fundamental aspect of the ongoing evolution of galaxies and the universe. They are the conduits through which galaxies exchange gas and dust, facilitating the recycling of material that forms the building blocks for future generations of stars and planets. While they may seem destructive at first glance, galactic winds ultimately contribute to the creation of new structures, ensuring the continued evolution of the cosmic landscape. In the broader context of cosmology, galactic winds provide valuable insights into the mechanics of the universe. They represent the ways in which energy and matter are exchanged and distributed throughout space. By studying these winds, we gain a better understanding of the forces that drive the evolution of galaxies, the formation of stars, and the development of cosmic structures. This knowledge helps us to better understand the complex, interconnected web of events that governs the life cycle of galaxies, and ultimately, the universe itself. The study of galactic winds is still in its early stages, and much work remains to be done. As our observational tools improve and our understanding of these cosmic phenomena deepens, we will continue to uncover new insights into the fundamental processes that shape the universe. The next few decades promise to be an exciting time for the study of galactic winds, as we gain a better understanding of their role in the grand cosmic narrative. As our understanding of galactic winds evolves, it's also crucial to consider their role in the grander cosmic cycles. These winds don't just affect the galaxies from which they originate, they can influence the evolution of the universe itself, contributing to the overall distribution of gas, energy, and matter across vast regions of space. A significant aspect of this is the role of galactic winds in regulating the amount of gas that can participate in future generations of star formation. The dynamics of how this gas is expelled, retained, or redistributed are key factors in the life cycles of galaxies. When a galaxy undergoes a massive starburst, driven by intense star formation, the stellar winds and supernovae resulting from these newly formed stars can generate a powerful outflow. These galactic winds can carry material away from the galaxy at speeds that can reach hundreds of kilometers per second. At these velocities, the winds are strong enough to strip the galaxy of large amounts of its gas, potentially halting or slowing further star formation. This type of feedback mechanism is central to regulating how long a galaxy can continue producing new stars. In some cases, the wind may eject a significant fraction of the galaxy's gas into the intergalactic medium, leaving the galaxy with insufficient material to form new stars. This can lead to what is known as a quenched galaxy, one that has ceased forming stars for a significant period. On the flip side, the expulsion of gas can also trigger new processes that enhance star formation. As the gas expelled by galactic winds interacts with the surrounding medium, it can be compressed, leading to the formation of new stars. This is a phenomenon that can occur in galaxies with active galactic nuclei, AGN, or other sources of powerful outflows. AGNs, in particular, play a dual role in this feedback process. While they are capable of producing vast amounts of energy that can expel gas and halt star formation, they can also provide energy to compress nearby gas, reigniting star formation in regions that might have otherwise remained dormant. This delicate balance between suppression and enhancement of star formation is central to the evolution of galaxies, influencing everything from the size and morphology of galaxies to their overall star formation rates. One fascinating aspect of galactic winds is how they influence the intergalactic medium. The intergalactic medium, IGM, is the gas that exists between galaxies, composed mostly of hydrogen and helium, but also containing traces of heavier elements. Galactic winds can inject material into the IGM, enriching it with elements forged in stars. This process is vital for the chemical evolution of the universe because it contributes to the pool of gas from which future galaxies can form. The chemical makeup of the IGM plays a critical role in the types of stars and galaxies that will form in the future. For example, regions of the IGM that are enriched with heavier elements may be more likely to form low-mass stars, as the presence of these elements plays a role in the cooling processes necessary for star formation. This distribution of material can also have profound effects on the large-scale structure of the universe. For instance, galactic winds that inject gas into the IGM can create vast, diffuse structures that extend across the space between galaxies. These large-scale structures, often referred to as the cosmic web, are composed of interconnected filaments of gas, dust, and dark matter. The winds that drive these outflows contribute to the shaping of this web, influencing the flow of matter across cosmic distances. This process plays a critical role in the formation of galaxy clusters, which are among the largest gravitationally bound structures in the universe. By redistributing gas across these vast distances, galactic winds help fuel the ongoing formation of stars and galaxies throughout the cosmos. To fully appreciate the significance of galactic winds, we must also consider their role in the context of the life cycle of supermassive black holes, SMBHs. At the centers of many galaxies, including our own Milky Way, lie these enigmatic, supermassive black holes. While black holes themselves are often associated with destructive forces, their role in galactic evolution is much more complex. Supermassive black holes are thought to grow by accreting gas from their surrounding environment, and as they do so, they can generate powerful jets of particles and radiation that drive galactic winds. These winds can either be a byproduct of the accretion process, or a direct result of the energetic outflows produced by the black hole's activity. In either case, the material expelled by these winds can have profound effects on the surrounding galaxy, influencing its rate of star formation, the distribution of gas, and even the formation of new black holes. The interplay between supermassive black holes, galactic winds, and their host galaxies is a key area of current research in astrophysics. Understanding how these winds are generated, how they propagate, and how they interact with the surrounding material is essential for comprehending the broader processes that govern the evolution of galaxies. In particular, the study of SMBHs and their feedback mechanisms is crucial for unlocking the mysteries of how galaxies grow and evolve over time. The discovery of active galactic nuclei and the observation of powerful outflows from these regions provide valuable clues about how these processes unfold on cosmic scales. Despite the wealth of knowledge we've gathered so far, there is still much to uncover about galactic winds and their role in the universe. For instance, much remains unknown about the exact physics behind the acceleration of the gas in these winds. How do winds achieve such high velocities? And what factors determine their speed and extent? How does the material ejected by supernovae or AGNs interact with the broader environment? And how does it contribute to the formation of large-scale cosmic structures? As astronomers continue to improve their observational techniques and develop more advanced models, we can expect to gain a deeper understanding of these phenomena. One promising avenue of research involves the study of galactic winds in distant, high-redshift galaxies. These galaxies, which formed in the early universe, provide a unique window into the conditions that prevailed during the early stages of galaxy formation. By observing how galactic winds operate in these distant galaxies, scientists hope to gain insights into the processes that shaped the earliest galaxies and the formation of the first stars. The study of these winds can provide valuable clues about the role of feedback in the evolution of galaxies and how the distribution of gas and matter in the early universe influenced the formation of larger cosmic structures. Another important area of research involves the potential for galactic winds to play a role in the overall fate of galaxies. In some cases, the expulsion of gas via galactic winds could eventually lead to the cessation of star formation within a galaxy, leaving it to fade away into a quiet, passive state. In other cases, the enrichment of the intergalactic medium with heavy elements could trigger the formation of new galaxies, creating fresh pockets of star formation across vast regions of space. These long-term effects highlight the dynamic, ever-changing nature of the universe, where galaxies are not static objects but active participants in the larger processes of cosmic evolution. Looking ahead, the continued exploration of galactic winds promises to shed light on some of the most profound mysteries of the universe. From the role of supernovae and black holes in shaping galaxy evolution to the interactions between galaxies and the broader intergalactic medium, galactic winds are central to understanding how the universe has evolved and continues to evolve. As new technologies and observational techniques come online, we can expect to uncover even more fascinating insights into the forces that drive galactic evolution and the role of galactic winds in shaping the cosmos. As we continue to explore the role of galactic winds in the evolution of galaxies and the universe, it's important to dive deeper into the complexities of these phenomena and their broader implications. Galactic winds not only impact the star formation rates within galaxies but also influence their overall morphology and the interplay between galaxies and larger cosmic structures. One significant consequence of galactic winds is their ability to redistribute mass within a galaxy. The violent expulsion of gas and dust during episodes of intense star formation or AGN activity can cause shifts in the galaxy's structure. This process can modify the distribution of stars, gas, and dark matter in a way that reshapes the galaxy over time. For example, galaxies that experience powerful winds might end up with a more diffuse stellar population, as the material that could have been used for future star formation is expelled into the intergalactic medium. Over time, this can lead to changes in the galaxy's color and its overall brightness, making it look older and less active. In some cases, galactic winds can even transform the galaxy's morphology. For example, a once spiral galaxy may lose its gas and dust content to such an extent that it becomes an elliptical galaxy, a much more passively evolving system. The removal of gas that could have been used to form new stars causes these galaxies to enter a phase of quiescence, where their stellar population ages without replenishment. This transformation is a fundamental aspect of galaxy evolution and is a direct consequence of the feedback mechanisms driven by galactic winds. In the broader context of galactic interactions, these winds can play a significant role in the processes that govern the dynamics of galaxy clusters. When galaxies collide or pass through one another in a dense environment, their gas and dust are often funneled into concentrated areas, triggering bursts of star formation or accelerating the activity of supermassive black holes. As these black holes generate powerful outflows, they can create galactic winds that influence the entire cluster. These winds may suppress star formation in some galaxies, while fueling it in others. Additionally, the material expelled into the intergalactic medium can lead to a gradual redistribution of gas across the cluster, influencing the formation of new galaxies and the evolution of the cluster as a whole. This larger-scale effect is particularly noticeable in galaxy clusters that exhibit significant amounts of hot gas. These clusters, which contain hundreds or thousands of galaxies, often feature a diffuse and extremely hot intergalactic medium, IgM, composed of plasma at temperatures of several million degrees Celsius. Galactic winds can inject cooler, enriched gas into this hot IgM, which has profound effects on the thermal and chemical properties of the cluster. For instance, the mixing of cooler gas with the hot IgM can lead to new forms of star formation, as the cooler material may provide the necessary conditions for gravity to overcome the pressure of the hot gas, triggering the collapse of clumps of gas into new stars. The process of galactic wind feedback also has implications for the growth of supermassive black holes. The interaction between winds and the surrounding material can provide an essential avenue for the energy generated by the black hole to escape. This feedback loop, where black hole activity generates galactic winds, which in turn suppress or enhance star formation, is one of the key drivers of galaxy evolution on both local and cosmological scales. As black holes grow and emit more energy, their winds may influence not only the galaxy they reside in but also nearby galaxies, either through direct interaction or by contributing to the broader intergalactic medium. The role of galactic winds in the chemical enrichment of the universe is another crucial aspect of their importance. The material expelled by these winds contains not just hydrogen and helium, but also heavier elements such as carbon, oxygen, and iron, elements that are forged in the cores of stars during their lifetimes and through explosive supernovae. These elements are vital for the formation of planets, and ultimately life. As galactic winds spread this material across the intergalactic medium, they enrich the IgM, making it a more complex, chemically diverse environment. This process is one of the reasons why the gas between galaxies is not just a simple mixture of hydrogen and helium, but a far more varied substance that influences the formation of future stars, galaxies, and even the larger structure of the universe. The interaction between galactic winds and the intergalactic medium is also responsible for some of the most spectacular and complex phenomena observed in deep space. One such example is the creation of bubbles, or cavities, in the IgM. These features, often associated with AGN-driven outflows, occur when the wind from an active black hole pushes gas away from the galaxy, creating vast regions of lower-density gas. These bubbles can extend across millions of light-years, and their study offers scientists valuable insight into the dynamics of the IgM and the forces at play in the evolution of galaxies. Additionally, these cavities can serve as indicators of the energy being injected into the IgM and help astronomers measure the impact of AGN feedback on the surrounding gas. One of the most pressing questions in current research is how to reconcile the different models of galactic wind dynamics. While we know that these winds are crucial for galactic evolution, there is still considerable uncertainty regarding the precise mechanisms by which they are accelerated and the full scope of their effects. Several models have been proposed to explain how these winds achieve their remarkable velocities, with one popular theory involving the heating and pressure from supernovae, which drive the wind outward. However, these models remain incomplete, as they must account for various factors, such as the structure of the wind, its interaction with the surrounding gas, and its long-term effects on the galaxy. Moreover, the physics of galactic winds varies significantly depending on the type of galaxy and the source of the wind. For example, in galaxies with a high rate of star formation, the winds are often driven by the energy released from massive stars and supernovae. These winds are relatively cool and contain a significant amount of molecular gas. On the other hand, in galaxies with an active galactic nucleus, the winds are much more energetic and are primarily composed of hot, ionized gas. The differences between these two types of winds highlight the complexity of the process and the need for more detailed simulations and observational studies. In the future, advancements in observational technology, particularly in the field of X-ray astronomy, will likely provide more detailed information about the behavior of galactic winds. Telescopes such as the upcoming James Webb Space Telescope, JWST, and the continued observations from the Chandra X-ray Observatory will provide critical data on the impact of these winds on galaxies and the intergalactic medium. These observations will allow us to track the movement of gas expelled by winds across large distances and, in doing so, enhance our understanding of how galaxies grow and evolve over time. Furthermore, as our ability to observe distant galaxies improves, we will be able to study galactic winds in environments that are not observable today. High redshift galaxies, which existed in the early universe, will provide unique insights into how galactic winds behaved during the formative stages of galaxy formation. These observations will help us understand how feedback processes in the early universe shaped the galaxies that would later give rise to the galaxies we see today. Galactic winds may also be a key factor in the ongoing search for life beyond Earth. As these winds expel essential elements into the intergalactic medium, they contribute to the broader chemical enrichment of the universe. This process ultimately affects the types of planets that can form in distant star systems, potentially influencing the habitability of those planets. Understanding how galactic winds distribute these elements across space could provide important clues in the search for extraterrestrial life and inform our understanding of how life might arise in other parts of the universe. As we continue to explore the fascinating realm of galactic winds and their profound impact on the universe, it's essential to consider their role in shaping the cosmic landscape on an even larger scale. Understanding the intricate interactions between galactic winds and the broader structure of the cosmos offers an incredible perspective on how the universe has evolved and continues to evolve. From the earliest stages of galaxy formation to the ongoing processes that govern galaxy clusters, galactic winds are at the heart of many cosmic transformations. One of the most intriguing aspects of galactic winds is their influence on the large-scale structure of the universe. The movement of gas and dust within galaxies, and between galaxies, plays a pivotal role in the formation of cosmic structures such as the cosmic web, a vast network of galaxy clusters and filaments that stretches across the universe. The feedback from galactic winds helps shape this cosmic web by redistributing gas, creating dense regions that give rise to new galaxies, and conversely, dispersing gas from older galaxies, slowing down star formation, and causing galaxies to dry out. The intergalactic medium, IgM, which is the gas between galaxies, is particularly sensitive to the effects of galactic winds. As winds expel gas and dust from galaxies, they contribute to the overall enrichment of the IgM, adding heavier elements such as metals, elements heavier than helium. This process, called chemical enrichment, is a critical factor in the development of the universe. The enrichment of the IgM enables the formation of second-generation stars, which are essential for building the complex structure of galaxies. As a result, the recycling of material within and between galaxies through galactic winds is fundamental to the creation of new stellar populations and the diversity of elements within the universe. Another fascinating effect of galactic winds is their role in regulating star formation across galaxies. As galactic winds carry away the gas and dust that could potentially fuel new stars, they effectively regulate the rate at which new stars are born within a galaxy. This feedback mechanism is essential for maintaining a balance between the formation of new stars and the rate at which old stars die. In galaxies with a high rate of star formation, the intensity of galactic winds can be so significant that they suppress star formation altogether, causing the galaxy to shut down its star-forming activity. Conversely, in galaxies with little ongoing star formation, the winds may provide just enough material to reignite star formation in certain regions, leading to bursts of stellar creation. At the same time, the outflows driven by supernovae and active galactic nuclei, AGN, also influence the properties of the supermassive black holes at the centers of galaxies. These outflows can help regulate the growth of the black hole itself by providing an outlet for excess material that would otherwise fall into the black hole. This interaction between black holes and their surrounding gas is a key aspect of what is known as AGN feedback. AGN feedback not only affects the black hole's growth but also impacts the surrounding galaxy by heating the gas in the vicinity, preventing it from cooling and collapsing into new stars. In this way, galactic winds and AGN feedback maintain a dynamic equilibrium that governs both the black hole and the galaxy. The interplay between galactic winds and the central black hole has important implications for the larger-scale environment of galaxy clusters. Galaxy clusters, which are vast collections of galaxies bound together by gravity, are constantly exchanging gas and dust through various processes, including the action of galactic winds. When a galaxy passes through a galaxy cluster, the pressure from the hot gas in the cluster can strip away the galaxy's gas, a phenomenon known as Ram pressure stripping. This removal of gas can significantly reduce the galaxy's ability to form new stars, a process that may contribute to the observed phenomenon of starless, or quenched, galaxies within clusters. However, galactic winds can also enhance star formation in certain contexts, especially in the gas-rich environments of young galaxies or in regions where the winds from one galaxy trigger the collapse of gas clouds in neighboring galaxies. These types of interactions can lead to a burst of star formation, which can, in turn, provide the necessary fuel for more galactic winds. In this way, galactic winds create a self-perpetuating cycle of stellar birth and death, fueling both the growth of galaxies and the evolution of the broader cosmic structure. The effects of galactic winds also extend to the behavior of dark matter within galaxies. Dark matter, the mysterious substance that makes up most of the mass of the universe, plays a crucial role in galaxy formation and dynamics. While dark matter itself is invisible and doesn't directly interact with normal matter, its gravitational influence is critical in shaping the structure of galaxies. The redistribution of gas and dust through galactic winds can influence the distribution of dark matter in a galaxy, altering the way in which dark matter halos are structured and affecting the overall gravitational pull of the galaxy. In addition to dark matter, galactic winds may play a role in the eventual fate of a galaxy. As winds expel gas into the surrounding intergalactic medium, a galaxy may eventually reach a point where it has lost enough material that it can no longer sustain significant star formation. This process is often referred to as gas depletion, and it can result in the galaxy evolving into a passive, red-ended system, where stars continue to age but no new stars are formed. These galaxies, often observed as elliptical or lenticular in shape, are an important part of the cosmic ecosystem, as they provide insights into the long-term evolution of galaxies and their transition from active, star-forming systems to more passive states. This transition is particularly important in understanding the evolution of the universe as a whole. Galaxies evolve over billions of years, and their interactions with galactic winds are a crucial factor in determining the paths they take. Whether a galaxy experiences rapid star formation followed by a shutdown of activity or a slow and steady growth, the influence of galactic winds is central to this process. These winds, in essence, regulate the entire life cycle of a galaxy, from its birth to its eventual decline, shaping not just individual galaxies but the structure of the universe itself. The study of galactic winds has profound implications for our understanding of the origins of the universe and the ultimate fate of galaxies. The processes that govern the movement of gas and dust across space are fundamental to the continued evolution of galaxies and their environments. As we improve our observational tools and theoretical models, we can better understand the role of galactic winds in shaping the cosmos. These winds not only provide a mechanism for the redistribution of material across space but also offer a window into the complex interactions that drive the evolution of galaxies and the universe at large. Looking forward, one of the most exciting areas of research in the study of galactic winds is the possibility of detecting these winds in distant, high-redshift galaxies. These galaxies, which existed when the universe was much younger, provide a unique opportunity to observe galactic winds in their infancy. By studying the way these winds behave in early galaxies, we can gain valuable insights into the processes that governed galaxy formation in the early universe and how these processes have evolved over cosmic time. Additionally, future observational missions, such as those using the James Webb Space Telescope, JWST, will allow us to study the effects of galactic winds on a much larger scale, providing a clearer picture of their role in shaping the universe we observe today. As our understanding of galactic winds continues to grow, it will undoubtedly lead to new insights into the nature of galaxy evolution, the behavior of supermassive black holes, and the complex interplay of forces that shape the universe. In the grand scheme of cosmic history, galactic winds are an essential part of the puzzle, shaping the galaxies we see today and the ones that will emerge in the future. Their study not only advances our understanding of the cosmos but also provides a deeper appreciation for the dynamic processes that govern the evolution of the universe. As we dive deeper into the continued exploration of galactic winds and their profound influence on cosmic evolution, we must consider the crucial role they play in both local and large-scale environments. These powerful outflows, propelled by the death of stars and the activity of supermassive black holes, provide key insights into the nature of the cosmos. The ongoing dynamics between these winds and their surrounding environments continue to reveal the complexity of galactic ecosystems and their impact on the future of the universe. One significant aspect of galactic winds that has sparked interest among astrophysicists is their potential contribution to the overall temperature and density of the intergalactic medium, IgM. The IgM, which constitutes the space between galaxies, is often extremely hot and diffuse, with its temperature reaching millions of degrees Celsius in many regions. When galactic winds expel hot gas into this medium, they can serve as a form of heating, increasing the thermal energy of the IgM. This process, known as feedback heating, occurs in various ways, including the release of energy from supernovae explosions and the high-energy jets emitted by active galactic nuclei, AGN. As these winds push gas and dust into the surrounding IgM, they not only heat the medium but also drive turbulence, which can lead to the mixing of different gas phases. This turbulence plays a critical role in the distribution of materials throughout the cosmic structure. It helps to prevent the gas from clumping too tightly, which could otherwise lead to the formation of large-scale structures like galaxy clusters at a much faster rate than observed. The feedback from galactic winds also helps smooth out the distribution of gas, acting as a form of regulation that ensures the IGM maintains a certain level of homogeneity over large scales. The wind's role in the suppression of star formation in some regions of the universe is another important factor in understanding the evolution of galaxies and clusters. In galaxies where supernovae are frequent, or where AGN activity is intense, galactic winds can exert pressure on the surrounding interstellar medium, ISM, preventing the cooling and condensation of gas necessary for new stars to form. This is part of a feedback loop that ultimately determines whether a galaxy will remain an active star-forming entity or transition into a quiescent, dead galaxy. However, galactic winds can also foster new waves of star formation, particularly when they interact with gas-rich environments. For example, in the outskirts of galaxies or in the merging of galaxies, the dispersal of gas can lead to shocks that trigger the collapse of gas clouds, resulting in a burst of star formation. These cycles of star formation and suppression, driven by galactic winds, are crucial in shaping the overall star formation history of the universe and give us insights into the broader processes that govern cosmic growth. Another fascinating aspect of galactic winds is their potential to influence the growth and activity of supermassive black holes. Supermassive black holes, which reside at the centers of most galaxies, are not only powerful sources of energy but also play an integral role in regulating the surrounding galaxy. As mentioned earlier, feedback from AGN activity can regulate the gas inflow into the black hole, preventing it from consuming too much material too quickly. This balance is essential in maintaining a stable galaxy, as excessive accretion could lead to the destabilization of the surrounding region. When a supermassive black hole's accretion disk becomes highly active, it can expel a significant amount of energy and material through relativistic jets, a process that can give rise to galactic winds. These winds, in turn, can regulate the growth of the black hole by carrying away gas that would otherwise be funneled into it. This delicate dance between accretion, feedback, and outflows ensures that black holes and galaxies remain in a balanced state, where neither the black hole nor the galaxy grows too large or too small too quickly. Over cosmic timescales, galactic winds play a vital role in determining the fate of individual galaxies. A galaxy's ability to continue forming stars and maintaining an active structure depends on the continuous balance between the material it can gather and what it loses through galactic winds. For galaxies that experience strong outflows, much of their gas may be lost to the surrounding medium, leaving them with limited fuel for future generations of stars. On the other hand, galaxies that manage to retain their gas are more likely to continue star formation, developing into more massive and complex structures over time. Galactic winds also have a significant impact on galaxy mergers. When two galaxies collide, their gas-rich regions interact in violent and spectacular ways. The result is often the ejection of vast amounts of gas into the intergalactic space, significantly altering the galaxy's structures and star formation activity. Depending on the nature of the merger, these interactions can either trigger a burst of star formation, known as a starburst, or lead to the depletion of star-forming material, leaving behind an older, more passive galaxy. Furthermore, galactic winds can play a pivotal role in the ultimate fate of galaxy clusters. These clusters, which consist of thousands of galaxies, are often surrounded by hot, ionized gas known as the intracluster medium, ICM. The interplay between galactic winds and the ICM is crucial for the energy dynamics of galaxy clusters. As galaxies within clusters expel gas through winds and AGN activity, they add material to the ICM, enriching it with metals and other elements that would otherwise be confined to the individual galaxies. This process contributes to the chemical evolution of the cluster as a whole. However, the outflows from individual galaxies within a cluster can also lead to the removal of gas from the galaxies themselves, particularly in the dense central regions of clusters. This process, known as strangulation, can lead to the gradual cessation of star formation in galaxies, as they lose the gas necessary to fuel new stars. Strangulation is often seen in galaxies at the center of clusters, where the environment is harsh, and the gravitational influence of nearby galaxies accelerates the loss of gas. Beyond the local effects, galactic winds also have a profound impact on the broader structure of the universe. As these winds eject gas and dust into the vast spaces between galaxies, they help distribute the elements that form the building blocks of stars, planets, and life itself. The process of enrichment that occurs as a result of these outflows ensures that the universe becomes progressively more complex over time, with heavier elements being spread throughout the cosmic void. This, in turn, allows for the formation of new generations of stars, some of which will eventually form planetary systems capable of supporting life. On the largest scales, the feedback mechanisms triggered by galactic winds influence the very fabric of cosmic evolution. These winds, through their interaction with the intergalactic medium and the intracluster medium, help to shape the large-scale structure of the universe. They contribute to the redistribution of matter, alter the temperature and density of gas, and regulate the rate of star formation, all of which play a significant role in the development of the cosmic web. The discovery and study of galactic winds have become an essential part of modern astrophysics, as they offer a key to understanding not only the evolution of galaxies but also the large-scale structure of the universe. With the advent of powerful telescopes, such as the James Webb Space Telescope, JWST, scientists are now able to observe these winds in greater detail than ever before. This new observational capability promises to unlock even more secrets about the role of galactic winds in shaping the universe and our understanding of cosmic evolution. Looking ahead, the continued exploration of galactic winds will undoubtedly lead to new revelations about the universe's past, present, and future. As our understanding of these phenomena deepens, we will gain greater insight into the forces that govern the cosmos and the intricate processes that have shaped the galaxies and stars we observe today. Galactic winds, once thought to be a secondary phenomenon, are now recognized as fundamental players in the grand narrative of the universe, influencing the evolution of galaxies, clusters, and the very fabric of the cosmos itself. As we dive deeper into the intricate processes involved in galactic winds, it becomes evident that their effects ripple through not just individual galaxies, but also across vast swaths of space. These winds, whether driven by the explosive death throes of stars or the violent activity of supermassive black holes, create a cosmic ecosystem where matter is constantly being redistributed, regulated, and transformed. The role of galactic winds in galaxy evolution is complex. While they can impede star formation by depleting gas, they can also foster new star birth by redistributing material. This delicate balance between destruction and creation determines the fate of galaxies over time. In some galaxies, particularly those in the early stages of evolution, galactic winds can be so strong that they expel nearly all of the gas needed for future star formation. This process is often referred to as blowout, and it leads to the cessation of star formation, resulting in a galaxy that grows old without producing new stars. On the other hand, there are galaxies where the winds can trigger a new cycle of star formation. In these cases, the winds sweep gas into dense regions, where it cools and condenses, ultimately leading to the formation of new stars. This cycle of feedback, where winds both hinder and help star formation, is essential to our understanding of how galaxies evolve. It underscores the notion that the universe is not a static place but one of constant transformation, where even the forces of destruction play a role in shaping the future. Galactic winds are also a key player in the overall chemical evolution of galaxies. As they expel gas and dust, they carry with them the heavy elements produced by previous generations of stars. This process, known as chemical enrichment, means that the gas in galaxies becomes progressively richer in metals over time. These elements, including carbon, oxygen, and iron, are the building blocks for planets and, eventually, life itself. As such, galactic winds are central to the process of making galaxies, and the universe as a whole, more complex over time. In the broader context of the universe, galactic winds contribute to the large-scale structure of the cosmos. When these winds push gas out into the intergalactic medium, they help redistribute matter across vast distances, affecting the formation of galaxy clusters and the intergalactic medium. The outflows from galaxies can enrich the IGM with metals, creating a more homogeneous distribution of elements across the universe. This enrichment process is vital for understanding the formation of the first stars and galaxies in the early universe. Moreover, Galactic winds are integral to the study of cosmic feedback, a concept that describes the interaction between the energy produced by stars, black holes, and other cosmic phenomena, and the interstellar and intergalactic environments in which they exist. Feedback processes, such as those driven by galactic winds, help regulate the growth of galaxies by controlling the inflow and outflow of gas. Without this regulation, galaxies could either grow too large or become starless and inert. The feedback loop ensures that galaxies remain in a dynamic state, constantly evolving as they exchange gas, dust, and energy with their surroundings. As our observational tools advance, scientists are uncovering more about the intricacies of galactic winds. One of the most exciting developments in recent years has been the ability to observe these outflows in real time using space-based observatories like the Hubble Space Telescope and, more recently, the James Webb Space Telescope. These observatories provide an unprecedented view of galactic winds, revealing their true nature and giving us a glimpse into the underlying processes that drive cosmic evolution. The role of galactic winds in shaping the universe is further emphasized by their influence on the cosmic web, the large-scale structure that connects galaxies across the universe. The cosmic web is made up of vast filaments of gas and dark matter, which connect galaxy clusters and form the backbone of the universe's structure. Galactic winds, as they propagate through these filaments, can influence the density and temperature of the gas, shaping the way galaxies and clusters interact with each other. In addition to their role in regulating the growth of galaxies, galactic winds are also believed to play a part in the formation of the first structures in the universe. In the earliest stages of cosmic history, the universe was filled with a hot, diffuse gas known as the primordial soup. This gas was composed primarily of hydrogen and helium, with only trace amounts of heavier elements. As the first stars began to form, they expelled massive amounts of energy and material through supernovae and stellar winds. These early galactic winds helped to shape the large-scale structure of the universe, seeding the formation of the first galaxies and clusters. As the universe continued to evolve, galactic winds remained a constant force, shaping the properties of galaxies and clusters over billions of years. In the present day, we can observe the effects of these winds in galaxies across a wide range of evolutionary stages. Some galaxies are in the process of forming new stars, while others are in the final stages of their evolution, with most of their gas depleted and their star formation activity halted. In each case, the role of galactic winds in regulating the flow of gas and energy is crucial in determining the future of the galaxy. One of the most profound questions in modern astrophysics is the role that galactic winds play in the large-scale fate of the universe. Will these winds eventually expel enough matter from galaxies to slow down or even halt star formation on a cosmic scale? Or will the continued cycling of gas and energy through galaxies lead to an eternal cycle of birth and death, with new stars and galaxies constantly forming, dying, and reforming in an ongoing cosmic drama? Another intriguing question is how galactic winds could be influencing the search for life in the universe. As galactic winds distribute elements across the cosmos, they contribute to the creation of the conditions necessary for life. The heavy elements expelled by stars during their life cycles and through supernovae are the very elements that make up planets, including those that may harbor life. As such, understanding the behavior of galactic winds is crucial not only for our knowledge of cosmic evolution but also for our quest to understand how life might arise on planets beyond our own solar system. The study of galactic winds continues to evolve, and with new technological advancements, scientists are poised to uncover even more about the complexities of these powerful forces. As we peer deeper into space, we are gaining a better understanding of how the universe has evolved, how galaxies interact, and how life may ultimately arise from the chaotic dance of stars, black holes, and winds that govern the cosmos. The ongoing exploration of galactic winds is a reminder of the dynamic and interconnected nature of the universe. Far from being isolated entities, galaxies and their winds are part of a larger, intricate web of cosmic phenomena that shape the fabric of space and time itself. As we continue to investigate the mysteries of galactic winds, we not only learn more about the past, present, and future of the universe but also gain insight into the fundamental processes that govern the cosmos. As we continue to explore the fascinating world of galactic winds, it's essential to understand how their influence extends across vast regions of space. The ability of these winds to shape the structure of the universe is not just a consequence of local forces within individual galaxies, but a process that links galaxies across enormous distances. In particular, galactic winds play a pivotal role in the ongoing exchange of matter between galaxies and the broader intergalactic medium, IGM. The IGM, a vast expanse of diffuse gas that fills the spaces between galaxies, acts as a reservoir for the expelled material from galaxies undergoing superwinds. This material, consisting primarily of gas and dust, is enriched with the heavy elements produced by stars and supernovae. The winds act as conduits, sending these elements into the IGM, thereby altering its chemical composition and influencing the conditions for future galaxy formation. Through this process, galactic winds have an indirect but profound impact on the future of galaxies and the structure of the universe itself. By dispersing matter into the IGM, they help fertilize this otherwise sparse and homogeneous medium, paving the way for the formation of new galaxies, star clusters, and potentially new planetary systems. The outflows from galaxies thus contribute to a cosmic recycling system, where matter is constantly being reprocessed and redistributed. These interactions between galaxies, their winds, and the IGM contribute to a larger, self-regulating cycle that governs the birth and death of galaxies over cosmic timescales. In particular, when galaxies experience intense periods of star formation, they produce copious amounts of gas and dust. However, this material does not remain bound within the galaxy for long. The strong winds produced by the star formation activity blow this material out into the surrounding space, where it may eventually settle into the IGM, or be absorbed by neighboring galaxies. At the same time, the inflow of new gas into galaxies, particularly from the IGM, can reignite star formation in regions where it has been stifled by previous outflows. This cycle of inflows and outflows, often referred to as galactic feedback, ensures that galaxies are not static entities but rather dynamic systems that evolve over time. It also means that the fate of any given galaxy is intrinsically linked to the surrounding cosmic environment, with galactic winds serving as a key mechanism for shaping its destiny. As we look further into the future, it becomes increasingly clear that the influence of galactic winds on the universe is far from a passive one. These winds do not merely redistribute gas and dust, they also play a role in regulating the energy balance of the cosmos. The energy released by supernovae, active galactic nuclei, AGN, and other high-energy phenomena is channeled into galactic winds, impacting the temperature and density of the surrounding space. This, in turn, affects the formation of large-scale structures like galaxy clusters and superclusters. The role of AGN in driving these winds is particularly noteworthy. Active galactic nuclei are thought to house supermassive black holes at their centers, which can generate immense amounts of energy as they consume nearby matter. This energy is released in the form of powerful jets and radiation, which can heat up the surrounding gas and propel it outward in the form of a superwind. These winds can be so powerful that they are capable of expelling entire gas reservoirs from the galaxy, effectively halting star formation for extended periods. In fact, many of the most massive and luminous galaxies in the universe have likely undergone such intense episodes of AGN-driven wind activity. These winds can quench star formation by preventing fresh gas from being able to cool and condense into new stars. However, they can also trigger a new era of star formation in regions outside the galaxy, where the expelled material cools and mixes with other intergalactic gas. The resulting interaction may lead to the creation of new galaxies, even as the original galaxy begins to lose its ability to form stars. What makes the study of galactic winds even more intriguing is the possibility that they may help resolve some of the long-standing mysteries of galaxy formation and evolution. For instance, the fact that many galaxies appear to have far less gas than their star-forming counterparts suggests that galactic winds might be playing a larger role in regulating star formation than previously thought. In particular, galaxies with central supermassive black holes and active nuclei might have been shut down by intense wind-driven feedback, transforming them into the so-called red and dead galaxies we see today. On a broader scale, galactic winds offer an explanation for the observed distribution of gas and metals in the universe. The chemical enrichment of the IgM is a critical process in the formation of the universe's large-scale structure. The outflow of material from galaxies via superwinds not only impacts the individual galaxies but also helps regulate the mixing of elements in the broader universe. Over billions of years, these processes will continue to shape the intergalactic medium and potentially pave the way for future generations of galaxies and stars. The cosmic significance of galactic winds is also reflected in their relationship with dark matter and dark energy, two of the most enigmatic substances in the universe. While dark matter cannot be directly observed, its gravitational influence is felt across vast distances. Galactic winds, in their role as drivers of large-scale gas movements, might offer indirect insights into the distribution of dark matter. For example, studying how winds interact with the dark matter halos that surround galaxies could provide clues to the underlying structure and behavior of this mysterious substance. Similarly, the way galactic winds influence the expansion of the universe is a fascinating area of study. If galactic winds can push gas into the IgM, altering its temperature and density, they could, in theory, play a role in the acceleration of cosmic expansion. This is especially intriguing in light of the ongoing mystery surrounding dark energy, the hypothetical force driving the accelerated expansion of the universe. While the full extent of these interactions remains unknown, the possibility that galactic winds are involved in this cosmic process is something that continues to intrigue astronomers and physicists alike. One of the most exciting areas of research in the study of galactic winds is the potential for discovering new types of cosmic phenomena. As scientists continue to observe distant galaxies with advanced instruments, such as the James Webb Space Telescope, we are likely to uncover new forms of galactic wind activity. This could involve the detection of winds emanating from galaxies at even earlier stages of evolution, providing a window into the conditions that existed shortly after the Big Bang. These early galactic winds could hold the key to understanding how the universe transitioned from a hot, dense state to the cooler, more structured cosmos we observe today. By studying these winds, scientists may be able to glean new insights into the formation of the first stars, the role of supermassive black holes in early galaxy evolution, and the dynamics of the early universe itself. Ultimately, the study of galactic winds is not just about understanding the local phenomena within individual galaxies. It is about gaining a deeper understanding of the broader processes that shape the universe, from the birth of stars to the evolution of galaxies and the formation of the cosmic structures that we see today. As we continue to study these powerful forces, we are bound to uncover new mysteries, solve old ones, and deepen our appreciation of the vast and ever-changing cosmos we inhabit. As we continue to dive deeper into the mysteries of galactic winds and their far-reaching implications, it's important to address the observational challenges that scientists face when studying these phenomena. The nature of galactic winds, driven by powerful supernovae, or the energetic processes around active galactic nuclei, AGN, makes them inherently difficult to observe directly. They often manifest as diffuse clouds of gas moving at extremely high velocities, which can blend seamlessly with their surrounding environments. This makes isolating and characterizing these winds a highly complex task. One of the primary methods for observing galactic winds is through the study of their effects on their surrounding gas. Astronomers rely heavily on spectroscopy to study the emission and absorption lines from the light that passes through or is emitted by the wind. These lines can reveal a great deal about the composition, velocity, and density of the gas involved. For example, the detection of broad and redshifted absorption lines in the spectra of distant galaxies often indicates the presence of high-velocity outflows, a hallmark of superwinds. Additionally, space-based telescopes like the Hubble Space Telescope and the more recently launched James Webb Space Telescope, JWST, provide a more detailed look at the complex structures of these winds. JWST, with its superior infrared capabilities, allows scientists to look further back in time than ever before, enabling the study of wind-driven feedback in galaxies from the early stages of the universe. This is an area of particular interest, as understanding the role of galactic winds in the early universe could provide insights into the formation and evolution of galaxies in their infancy. On the ground, Astronomers also use powerful ground-based telescopes and observatories, such as the Very Large Telescope, VLT, and the Atacama Large Millimeter/Submillimeter Array, ALMA, to capture the intricate details of galactic winds. By focusing on specific wavelengths of light emitted by gas in these outflows, they can map the distribution of material expelled by galaxies. This has led to groundbreaking discoveries, such as the detection of massive outflows in star-forming galaxies, some of which extend hundreds of thousands of light-years from their host galaxies. These outflows are thought to play a significant role in shaping the galaxy's future, determining how much gas is available for future star formation. Beyond simply observing the winds themselves, scientists have also been developing more sophisticated simulations and computational models to predict and understand their behavior. These simulations take into account the myriad factors that influence galactic winds, from the gravitational pull of a galaxy's dark matter halo to the intense radiation pressure exerted by supernovae and the central black hole. By running these simulations on powerful supercomputers, researchers can better predict the evolution of galactic winds and their impact on galaxy formation, star formation, and even the large-scale structure of the universe. One aspect of galactic wind research that has gained significant attention in recent years is the study of the impact these winds have on the galaxies that generate them. In particular, the energy released by these winds can dramatically alter the properties of the galaxy. For instance, the dispersal of gas from a galaxy can quench star formation by removing the raw material needed to form new stars. This is especially true for galaxies with powerful active galactic nuclei, AGN. When these supermassive black holes at the centers of galaxies become highly active, they can expel vast amounts of gas through relativistic jets and outflows. This process can stop star formation in its tracks, turning what was once a vibrant, star-forming galaxy into a red and dead galaxy, where star formation has effectively ceased. The feedback mechanisms at play in these systems are complex. In some cases, the winds from supernovae or AGN can regulate the star formation rate of the galaxy, preventing it from creating too many stars too quickly. This is crucial because if too many stars are formed in a short amount of time, the galaxy can run out of its available gas, making it unable to form new stars in the future. On the other hand, by expelling gas into the intergalactic medium, IGM, galactic winds can also fuel future generations of star formation in other parts of the universe. This can lead to the formation of new galaxies or even spark the creation of new star clusters in distant regions of the cosmos. In addition to their impact on individual galaxies, galactic winds have a profound influence on the intergalactic medium, IGM. As previously mentioned, these winds help to enrich the IGM with heavy elements produced by dying stars. This process, called galactic chemical enrichment, alters the composition of the gas in the IGM, making it more conducive to future star formation. Without these winds, the IGM would remain composed mostly of hydrogen and helium, the primordial elements left over from the Big Bang. It's through the work of galactic winds that the universe has become enriched with the elements necessary for the formation of rocky planets and complex life as we know it. This cosmic recycling of material is an ongoing process that has been shaping the universe for billions of years. The distribution of metals in the IGM is critical for the formation of new stars and galaxies. As winds from older galaxies spread out into the IGM, they contribute to the creation of the cosmic web, the large-scale structure of the universe made up of interconnected filaments of dark matter and gas. The material expelled by winds can collect in these filaments, leading to the formation of new structures, star clusters, and even entire galaxies. On a larger scale, the role of galactic winds in the cosmic evolution of the universe cannot be understated. By driving material out of galaxies and into the IGM, these winds contribute to the ongoing process of cosmic evolution, affecting how galaxies grow and evolve. The exchange of matter between galaxies and the IGM creates a dynamic environment that constantly reshapes the distribution of gas and dust in the universe. Over billions of years, these outflows have played a significant role in shaping the cosmic landscape, contributing to the formation of galaxy clusters and the development of large-scale structures that we observe today. As we look to the future, the study of galactic winds is likely to reveal even more profound mysteries about the nature of the universe. With new observational tools, such as the upcoming upgrades to the James Webb Space Telescope and advancements in ground-based observatories, scientists will be able to peer deeper into the cosmos and study these powerful winds in unprecedented detail. It is through these observations that we will gain a more complete understanding of how galaxies evolve, how stars form, and how the universe itself continues to evolve over time. Moreover, the ongoing study of galactic winds may help solve some of the most fundamental questions in cosmology. For example, understanding how galactic winds affect star formation rates and galaxy growth can shed light on the fate of our own Milky Way. Will the supermassive black hole at its center eventually drive the galaxy's star formation to a halt, or will it continue to birth new stars for billions of years to come? And how will the material ejected by these winds continue to shape the intergalactic medium, potentially triggering the birth of new galaxies far from the site of the original outflow? Ultimately, the study of galactic winds reveals not only the inner workings of individual galaxies, but also the broader processes that shape the universe itself. From the birth of stars to the formation of galaxies and the ongoing evolution of the cosmos, galactic winds are an integral part of the grand cosmic story. As our understanding of these winds continues to grow, so too will our understanding of the universe. A universe that is dynamic, interconnected, and constantly evolving. As we explore further, it's important to consider the unique role that galactic winds play in the broader context of the universe's life cycle. These winds are not just a byproduct of cosmic events, but rather, they are critical mechanisms that influence the future of galaxies. In fact, the very process of galactic evolution itself can hinge on the intensity and nature of these outflows. The interplay between the energy released by star formation, supernovae, AGN, and the galactic winds that are driven by them often determines the trajectory of a galaxy's development, including whether it will remain a thriving star-forming region or transition into a more passive, evolved state. The question of how long a galaxy can sustain its ability to form new stars is of particular importance. The supply of cold gas, the raw material necessary for star formation, is key to a galaxy's continued activity. When galactic winds expel this material, the galaxy's star formation rate can be dramatically slowed, and in extreme cases, it can be halted altogether. This is often seen in galaxies that are considered quenched, meaning that they have exhausted the gas needed to form new stars. Understanding the role of galactic winds in this process allows astronomers to gain insight into the long-term evolution of galaxies, including the fate of our own Milky Way. In addition to quenching star formation, galactic winds also play a key role in the regulation of the mass of galaxies. By removing gas from a galaxy, these winds can limit the total mass available for future star formation. This has important implications for the mass-to-light ratio of a galaxy, which is a fundamental property used by astronomers to study galaxy evolution. Essentially, the more gas a galaxy loses through these outflows, the less it can grow in size and mass. As a result, galaxies that experience particularly powerful outflows may never reach the size of galaxies that retain their gas and continue to form stars. But it's not just about the galaxies themselves. Galactic winds have a profound effect on the broader cosmic environment, especially on the intergalactic medium, IGM. As these winds eject gas and metals into the surrounding voids, they contribute to the complex structure of the universe. The IGM, which was once thought to be a relatively simple, uniform environment, is now known to be a highly dynamic region, influenced by the interactions between galaxies and their winds. This dispersal of elements, particularly heavy elements like oxygen, carbon, and iron, is critical for the chemical enrichment of the IGM. Without these winds, the intergalactic space would remain largely devoid of the metals necessary for the formation of complex structures, including planets, stars, and potentially even life. These winds are the cosmic vehicle for dispersing the building blocks of life throughout the universe. In this way, galactic winds are not just the agents of destruction but also the architects of new worlds and new generations of stars. One of the most fascinating aspects of galactic winds is their relationship with the supermassive black holes at the centers of galaxies. Active galactic nuclei (AGN) are regions surrounding these black holes that are incredibly energetic. When a supermassive black hole accretes material, it generates enormous amounts of energy, much of which is channeled into powerful jets and outflows of material. These outflows, which can reach velocities close to the speed of light, can impact not just the galaxy hosting the black hole, but the larger-scale structure of the universe itself. The feedback from AGN can create what are known as AGN-driven winds. These winds are not only able to expel gas from their host galaxies, but they can also interact with the surrounding cosmic environment, heating the intergalactic medium and preventing the cooling of gas that is necessary for new star formation. In some cases, the energy released by these winds can halt the process of cooling and condensation, effectively stalling the cycle of star formation. This feedback loop between AGN and galactic winds is one of the primary mechanisms that regulates galaxy evolution, often creating a balance between star formation and the expulsion of material. But there's more to the story. AGN-driven winds are not only responsible for shutting down star formation within their host galaxies, but can also affect galaxy clusters. The energy and material expelled from individual galaxies can accumulate and spread across the entire cluster, influencing the formation and growth of galaxies within that cluster. In some instances, these winds can be so powerful that they reshape the structure of the cluster itself, creating an environment in which new galaxies may form, or existing galaxies may be stripped of their gas. As we delve deeper into the role of galactic winds, it becomes clear that these phenomena are deeply connected to the fundamental processes governing galaxy formation and evolution. The interaction between star formation, supernovae, AGN, and galactic winds forms a complex feedback system that governs not just the fate of individual galaxies, but the evolution of the entire universe. These winds are a critical piece of the puzzle that helps us understand how galaxies grow, mature, and eventually evolve into the galaxies we observe today. Furthermore, the study of galactic winds extends beyond the field of astronomy and into cosmology. By studying these winds and their effects on galaxies, scientists can learn about the larger-scale dynamics of the universe, including the distribution of matter, the evolution of cosmic structures, and even the fundamental processes that govern the formation of the universe itself. The winds of galaxies, it turns out, are more than just powerful outflows of gas. They are key to understanding the ongoing story of the universe's expansion and its ultimate fate. As observational technology continues to improve, the field of galactic wind research is only going to expand. With advancements in both ground-based and space telescopes, such as the upcoming ELT, Extremely Large Telescope, and future space missions, astronomers will be able to probe the details of these winds in unprecedented detail. The ability to observe galactic winds in different wavelengths, from radio to optical to X-ray, will allow scientists to develop a more comprehensive understanding of how these winds operate and how they influence their environments. One exciting frontier in galactic wind research involves the study of outflows in distant, high-redshift galaxies. These galaxies, which existed billions of years ago, are seen as they were in the early stages of their formation. Studying the winds in these galaxies could provide critical insights into how galaxies evolved in the early universe, offering a glimpse into the conditions that shaped the cosmos as we know it today. The high-energy processes occurring in these galaxies, such as supernovae and AGN activity, may have been much more intense in the past, leading to even more powerful winds. Understanding how these early galactic winds shaped the universe's development could be crucial for understanding the origins of galaxies, stars, and even life itself. Additionally, the role of galactic winds in large-scale cosmic structures like galaxy clusters and cosmic voids remains a topic of active research. These large-scale structures are the largest known objects in the universe, and understanding how galactic winds contribute to their formation and evolution is crucial for understanding the full extent of cosmic evolution. Galactic winds may play an essential role in shaping the cosmic web, the vast network of interconnected galaxies and intergalactic gas that makes up the fabric of the universe. As we continue our exploration of galactic winds, we must not overlook their impact on the broader intergalactic medium, IGM, the vast, mostly empty spaces between galaxies. These regions of space, long considered devoid of significant matter, are actually teeming with an intricate web of gas and dark matter. Galactic winds, through their expulsion of gas and metals, play a key role in shaping this medium, creating an environment that is far from static. When galactic winds expel material into the IGM, they do so in a manner that is not only energetic but also far-reaching. These winds can inject large amounts of gas and metals, enriching the IGM with elements heavier than hydrogen and helium, elements essential for the formation of planets and, ultimately, life. Without this enrichment, much of the IGM would remain barren of the elements needed to create complex structures, from rocky planets to stars with their diverse elemental compositions. The distribution of these elements across the IGM also plays a crucial role in understanding the chemical evolution of the universe. One of the most fascinating aspects of this process is how the expelled material from galactic winds interacts with the already existing gas in the IGM. The winds often cause shock waves that heat the surrounding gas, pushing it to extremely high temperatures, sometimes millions of degrees Celsius. This heating process can prevent the gas from cooling and collapsing to form new stars, a process known as feedback suppression. In essence, the galactic winds can inhibit the formation of new stars in their host galaxy, as well as in the surrounding regions of the universe. This feedback mechanism is a fundamental component in regulating the rate of star formation in galaxies and the growth of the cosmic web. Additionally, the interaction between galactic winds and the IGM can lead to the formation of new cosmic structures, including the creation of bubbles, or voids in the gas. These voids are vast regions of space that are relatively empty compared to the surrounding areas, and they are a key feature of the large-scale structure of the universe. As galactic winds expel gas and metals into the IGM, they can push the gas outwards, creating these bubbles and altering the distribution of matter on a cosmic scale. Understanding the role of galactic winds in this process helps astronomers trace the growth and evolution of the universe's large-scale structures. Moreover, the study of galactic winds in the context of the IGM provides valuable insights into the ongoing mystery of cosmic reionization. This event, which took place about 1 billion years after the Big Bang, saw the universe transition from a state where the gas was neutral to one where it was ionized. The process of reionization is thought to have been driven by the first generations of stars and black holes, whose intense radiation and energetic outflows helped to ionize the surrounding gas. The contribution of galactic winds to this process, and how they might have shaped the IGM during reionization, is a question that remains actively researched. Understanding how galactic winds interact with the IGM during this critical period could help solve one of the most significant puzzles in cosmology: the nature of the early universe and the forces that shaped its evolution. The impact of galactic winds on galaxy clusters is another area of active research. Galaxy clusters, which are the largest gravitationally bound objects in the universe, are vast structures that contain hundreds or even thousands of galaxies. The interplay between these galaxies and the winds they generate can shape the entire cluster's dynamics. In some cases, galactic winds from galaxies in a cluster can merge and form large-scale outflows that affect the cluster as a whole. These outflows can even reach across the cluster, affecting the intergalactic medium within it and influencing the overall behavior of the cluster. For instance, galactic winds can contribute to the stripping of gas from galaxies, altering the amount of cold gas available for future star formation. In some scenarios, these outflows can even push material out of the cluster entirely, dispersing it into the larger voids between galaxy clusters. The role of galactic winds in the larger-scale evolution of galaxy clusters offers a new perspective on how these immense cosmic structures evolve and interact. By studying the behavior of galactic winds in the context of galaxy clusters, astronomers are gaining a better understanding of the interconnectedness of galaxies and how they influence one another across vast cosmic distances. What's even more intriguing is that these galactic winds are not just driven by local processes such as star formation and AGN activity. In fact, the winds can also have long-term effects that stretch across vast distances, potentially influencing galaxies far beyond the host galaxy's immediate vicinity. These winds can travel through intergalactic space and affect the surrounding galaxies, modifying their environments in ways that we are just beginning to comprehend. To fully grasp the significance of these winds, we must also consider the observational challenges that come with studying such phenomena. Observing galactic winds is no easy task, as they are often diffuse and faint, making them difficult to detect against the backdrop of brighter, more dominant structures like the stars and the supermassive black holes at the centers of galaxies. However, advancements in technology have allowed astronomers to study these winds in greater detail. Tools like the Hubble Space Telescope, the Chandra X-ray Observatory, and the upcoming James Webb Space Telescope provide new opportunities to observe these galactic outflows across multiple wavelengths of light. For instance, the detection of galactic winds in X-rays is particularly important because it allows scientists to study the high-energy processes that drive these winds. When material is expelled at high velocities, it often becomes ionized and emits X-rays, which can be detected by specialized telescopes. These observations help astronomers map the distribution of gas and dust in and around galaxies, providing crucial data on how these winds evolve and interact with their environments. Radio telescopes are also a key tool in the study of galactic winds. These instruments can detect the presence of synchrotron radiation, which is emitted when high-energy particles are accelerated by the magnetic fields associated with galactic outflows. By observing the radio emissions from these regions, scientists can trace the motion of charged particles and gain insights into the mechanics of these winds. Additionally, the detection of molecular gas in the form of CO emissions in galaxies can reveal the conditions under which stars are forming and how these winds are interacting with the cold gas present in the galaxy. As the observational capabilities of these telescopes improve, we will undoubtedly gain even deeper insights into the processes that drive galactic winds. This will allow for a more complete understanding of the complex mechanisms that govern galaxy evolution, the growth of cosmic structures, and the very nature of the universe itself. Galactic winds are much more than simple outflows of gas and dust. They are integral to the evolution of galaxies, the shaping of the intergalactic medium, and the overall structure of the universe. Their impact on star formation, galactic growth, and the dispersal of elements into the cosmos is profound and far-reaching. As astronomers continue to refine their understanding of these winds, they are uncovering a more intricate picture of the forces that govern the universe. Through the study of galactic winds, we not only gain insight into the life cycle of galaxies but also into the very processes that have shaped the universe from its earliest moments to its current state. With continued advancements in observational technology and theoretical models, the study of galactic winds will undoubtedly play a pivotal role in unraveling some of the deepest mysteries of the cosmos. By understanding the forces that drive these winds and the ways they shape the galaxies around us, we can gain a better understanding of the universe's past, its present, and its future. In many ways, the winds of the cosmos carry with them the secrets of the universe itself. As we move forward in our exploration of galactic winds, it's crucial to consider their broader cosmological implications, particularly in the context of the universe's evolution. Galactic winds, although often studied within the boundaries of individual galaxies, have far-reaching consequences for the larger cosmic landscape. These winds are not just isolated phenomena. They are key players in the ongoing dance between galaxies, stars, gas, and dark matter that shapes the universe. One of the most intriguing aspects of galactic winds is their connection to the overall process of galaxy formation and evolution. For much of cosmic history, galaxies were considered primarily as isolated systems, their growth and evolution determined mainly by the material available within them. However, the discovery of galactic winds has forced astronomers to reconsider this view, suggesting that galaxies are not self-contained units, but are actively shaped by external forces. These winds help to redistribute material on a galactic scale, influencing not only the host galaxy but also the surrounding galaxies and the intergalactic medium. The role of galactic winds in shaping the overall structure of the universe is linked to a broader process known as galactic feedback. This term refers to the way in which the energy and material released by stars, supernovae, and AGN influence the gas and dust within and around galaxies. Galactic feedback can take many forms, from star formation suppression to the triggering of new star formation in other regions. Supernovae, for instance, can release vast amounts of energy into their surrounding environment, triggering shockwaves that compress nearby gas clouds and potentially leading to new star formation. However, these same supernovae can also expel gas from their host galaxy, reducing the available material for future star formation. In this sense, galactic winds act as both creators and destroyers, facilitating the formation of new stars in one area while stripping away material from another. Understanding the feedback processes associated with galactic winds is critical for comprehending the growth of galaxies across cosmic time. In the early universe, galaxies were primarily fueled by intense bursts of star formation, often referred to as starbursts. During these periods of rapid star formation, the energy released by young, massive stars and their supernovae would create powerful galactic winds, expelling gas and metals from the host galaxy. This process helped regulate the rate of star formation, ensuring that the galaxy did not consume all of its gas too quickly. Over time, as galaxies aged and their rate of star formation slowed, the feedback from galactic winds became a critical factor in shaping their evolution. The interaction between these winds and the galaxy's gas reservoir helped determine whether the galaxy would continue forming stars at a steady pace or whether it would evolve into a more quiescent, passively evolving system. Galactic winds also play a significant role in shaping the large-scale structure of the universe. As material is expelled from galaxies, it spreads out into the intergalactic medium, enriching it with heavy elements. This process of enrichment is crucial for the formation of future stars and galaxies. The spread of these elements into the IGM also contributes to the overall chemical evolution of the universe. The more material that is expelled from galaxies, the more it impacts the environment in which future galaxies will form. This process has profound implications for our understanding of the history of star formation and the spread of life-essential elements across the cosmos. Furthermore, the interaction between galactic winds and the IGM can help us understand the complex relationships between dark matter and visible matter. Although dark matter does not directly interact with galactic winds in the way that gas and dust do, its gravitational influence plays a crucial role in shaping the motion and behavior of these winds. The presence of dark matter in and around galaxies helps to channel the winds, guiding their trajectory and determining the areas of space where they are most likely to be expelled. This interaction between dark matter and visible matter provides valuable clues about the distribution of dark matter in the universe, a topic that remains one of the biggest mysteries in modern astrophysics. Another aspect of galactic winds that warrants further investigation is their role in the formation and evolution of galactic halos. These halos, which are made up of hot gas and dark matter, surround many galaxies and play a key role in the dynamics of the galaxy itself. The gas within these halos is often heated by the energy from supernovae and AGN activity, creating a hot, diffuse atmosphere that extends far beyond the galaxy's visible structure. Galactic winds, by transporting material into and out of these halos, contribute to the heating and cooling processes that govern the behavior of the gas within. This process can have significant implications for the growth of galaxies, as it helps regulate the amount of cold gas available for star formation. In addition, galactic winds can help shape the distribution of galaxies across the universe. As winds expel material from one galaxy, they can influence the gas and dust in nearby galaxies, triggering the collapse of gas clouds and potentially sparking the formation of new stars. These interactions between galaxies, driven by their mutual outflows, can lead to the creation of galaxy groups and clusters, further shaping the large-scale structure of the universe. One of the most profound consequences of galactic winds is their potential role in regulating the expansion of the universe. As these winds release vast amounts of gas and energy into the IGM, they contribute to the overall energy budget of the universe. The redistribution of energy and matter throughout the cosmos could have long-term effects on the universe's expansion rate. Understanding the role of galactic winds in this context could provide key insights into the ultimate fate of the universe, shedding light on questions such as the nature of dark energy and the future growth of cosmic structures. As we delve deeper into the study of galactic winds, we are presented with an increasingly complex and dynamic picture of the universe. These winds are not simply a local phenomenon, but rather a critical piece of the larger puzzle that governs the evolution of galaxies, stars, and the universe as a whole. Through the continued study of galactic winds, we are not only uncovering new details about the processes that drive galactic evolution but also gaining a deeper understanding of the fundamental forces that shape the cosmos. In the future, advances in observational technology will likely allow for even greater insights into the nature of galactic winds. New telescopes, such as the James Webb Space Telescope, promise to provide unprecedented views of galaxies and their outflows, offering a clearer picture of how these winds interact with their environments. As astronomers continue to probe the mysteries of galactic winds, we can expect to uncover even more fascinating details about the evolution of galaxies, the growth of cosmic structures, and the ongoing interplay between matter, energy, and the forces that shape the universe. Galactic winds are a critical, dynamic force in the universe, influencing everything from the formation of stars to the large-scale structure of the cosmos. Through their intricate interaction with galaxies, the intergalactic medium, and even dark matter, these winds shape the universe in ways we are only beginning to understand. Their study not only deepens our knowledge of cosmic evolution but also brings us closer to understanding the complex forces that govern the universe itself. As we look to the future of galactic wind research, one area of great interest lies in the potential for studying these winds in distant galaxies. The majority of observations so far have focused on relatively nearby galaxies, where the effects of galactic winds can be observed in more detail. However, the true power of these winds can be fully appreciated when we look at galaxies across vast distances, galaxies that formed billions of years ago during the early stages of the universe's evolution. By studying these distant galaxies, astronomers hope to unravel how galactic winds have shaped galaxy formation and evolution over cosmic time. One exciting area of research is understanding how galactic winds impacted the first galaxies that formed in the early universe. These ancient galaxies, often called first light galaxies, are thought to have formed during a period known as the cosmic dawn, roughly a billion years after the Big Bang. During this time, the first stars and black holes began to form, and their powerful radiation and explosions may have triggered intense galactic winds. These winds would have had a profound impact on the surrounding gas and dust, potentially inhibiting the formation of new stars in the host galaxy or triggering a wave of star formation in nearby regions. By studying the effects of galactic winds in these early galaxies, we can gain insight into the conditions that existed during the universe's formative years, offering a deeper understanding of the processes that shaped galaxies at their birth. The study of galactic winds also holds promise for advancing our understanding of black hole evolution. Active galactic nuclei (AGN), the supermassive black holes that lie at the centers of many galaxies, are key players in driving galactic winds. These black holes can produce vast amounts of energy in the form of jets and radiation, which in turn fuel the outflows of gas and dust that make up the winds. The energy output from these AGN not only affects the evolution of their host galaxies but also provides crucial information about the growth of black holes themselves. By studying the interaction between galactic winds and AGN, astronomers can learn more about the processes that govern black hole growth, including how they acquire their massive size and how they influence their surrounding environment. In addition to AGN, the role of supernovae in driving galactic winds is another key area of research. Supernovae, the explosive deaths of massive stars, are some of the most energetic events in the universe. The shockwaves produced by these explosions can accelerate material to extremely high velocities, expelling gas and dust from the galaxy in the process. These supernova-driven winds can also contribute to the enrichment of the intergalactic medium, spreading heavy elements across vast distances. In fact, the very presence of heavy elements in the universe, the elements necessary for the formation of planets, life, and even galaxies themselves, can be traced back to these explosions. By studying the chemical makeup of galactic winds, scientists can gain a better understanding of the history of element formation in the universe and how the products of stellar death have influenced the formation of new stars, galaxies, and even life. Another avenue for future exploration is the role of galactic winds in the formation and evolution of galaxy clusters. These clusters, which contain hundreds or even thousands of galaxies, are among the largest structures in the universe. The interaction between galaxies within a cluster can drive complex processes, including the exchange of gas and dust between galaxies. Galactic winds play a crucial role in these interactions, influencing the dynamics of the cluster as a whole. For example, winds from one galaxy may be absorbed by another, triggering a burst of star formation or contributing to the stripping of gas from a galaxy's outer regions. By studying the effects of galactic winds within clusters, astronomers can learn more about the processes that govern the formation of these massive structures and how they evolve over time. The future of galactic wind research is also closely tied to advancements in observational technology. Current telescopes, such as the Hubble Space Telescope, have provided invaluable insights into the behavior of galactic winds, but they are limited in their ability to observe distant galaxies and the high-energy phenomena associated with these winds. Upcoming missions, like the James Webb Space Telescope, JWST, are poised to revolutionize our understanding of galactic winds by providing deeper, more detailed observations of galaxies at various stages of their evolution. The JWST's advanced infrared capabilities will allow astronomers to study the interaction between galactic winds and the surrounding gas in unprecedented detail, revealing new information about the processes that drive galaxy growth and evolution. Additionally, the upcoming launch of ground-based observatories, such as the Extremely Large Telescope, ELT, in Chile, promises to provide even more powerful instruments for studying the gas flows within and around galaxies, allowing scientists to observe galactic winds in far greater detail than ever before. On a larger scale, studying galactic winds could also help address some of the biggest unanswered questions in cosmology, such as the nature of dark matter and dark energy. While dark matter is invisible and does not interact with light, its gravitational influence can be detected through its effects on visible matter. The presence of dark matter in and around galaxies affects the motion of gas, stars, and even galactic winds. By studying how galactic winds behave in the presence of dark matter, scientists can learn more about the distribution of dark matter within galaxies and across the universe. In a similar vein, galactic winds could help improve our understanding of dark energy, the mysterious force responsible for the accelerated expansion of the universe. As galactic winds redistribute material throughout the cosmos, they contribute to the overall energy budget of the universe, potentially offering clues about the role of dark energy in the universe's evolution. The influence of galactic winds also extends to more exotic phenomena, such as the role of winds in the formation of intergalactic filaments. These vast, thread-like structures of dark matter and gas stretch across the universe, connecting galaxy clusters and forming the backbone of the cosmic web. Galactic winds, driven by supernovae, AGN, and other energetic events, contribute to the formation and evolution of these filaments, helping to shape the large-scale structure of the universe. By understanding how galactic winds interact with these filaments, astronomers can gain insights into the forces that shape the cosmic web and the evolution of large-scale structures across the universe. Galactic winds are among the most fascinating and important phenomena in the universe, playing a key role in shaping the evolution of galaxies, the distribution of gas and dust, and the large-scale structure of the cosmos. These winds, driven by supernovae, AGN, and other energetic events, are not isolated processes but are deeply connected to the fundamental forces that govern the universe. From influencing star formation to regulating the growth of galaxies and galaxy clusters, galactic winds are crucial players in the ongoing cosmic drama. As our observational capabilities continue to improve, we are bound to uncover even more about these powerful, far-reaching winds and their role in the ongoing evolution of the universe. Through continued research, we are not only deepening our understanding of the forces that shape galaxies but also gaining invaluable insights into the broader processes that govern the evolution of the cosmos itself. The future of galactic wind research holds even more promise as we move into the realm of more detailed simulations and computational models. These tools will allow astronomers to model the complex interactions between galactic winds and their environments in ways that were previously impossible. The intricacies of how winds affect star formation, the movement of gas, and the shaping of galactic structures can be examined in greater depth, providing insights that can be compared with real-world observations. For example, simulations could help us predict how winds behave in different types of galaxies, whether a spiral galaxy, an elliptical galaxy, or a more irregular shape, and how these winds affect the gas, dust, and stars within them. One of the most exciting aspects of future research is the development of high-resolution simulations that incorporate the effects of magnetic fields, turbulence, and cosmic rays. These additional factors play a critical role in the dynamics of galactic winds. Magnetic fields, for instance, can affect the way gas and dust are expelled from a galaxy, potentially altering the speed and direction of the wind. Cosmic rays, high-energy particles that are created in supernova explosions and other high-energy events, can also influence galactic winds by contributing to the heating of the gas and even affecting the way that gas is transported across vast distances. By including these factors in simulations, scientists can achieve a more accurate and detailed picture of how galactic winds shape the universe. The advancement of machine learning and artificial intelligence in the study of galactic winds also holds great potential. These technologies can be used to sift through vast amounts of data from telescopes, quickly identifying patterns and correlations that would be impossible for humans to discern on their own. Machine learning algorithms can analyze the spectra of distant galaxies, identifying the chemical compositions and velocities of galactic winds with unprecedented precision. These algorithms can also be used to improve simulations, optimizing parameters based on real-world observations and ensuring that the models reflect the true complexity of the phenomena being studied. As more data becomes available from new space missions and observatories, machine learning will become an invaluable tool in the quest to understand the intricate role of galactic winds in the cosmic landscape. Moreover, the study of galactic winds is inextricably linked to our understanding of the larger galactic environment, including the phenomenon known as feedback. Feedback refers to the process by which a galaxy influences its surroundings, and vice versa, in a cycle of exchange. Galactic winds are a crucial component of this feedback loop, as they not only distribute gas and dust but can also suppress or stimulate star formation in their host galaxy. For example, powerful winds may strip a galaxy of its gas, preventing new stars from forming, or they may compress gas in other parts of the galaxy, leading to an influx of new stars. This feedback process has a profound impact on the overall evolution of a galaxy, and understanding the mechanisms behind it is one of the key objectives in modern astrophysics. Feedback is also closely related to the growth and evolution of supermassive black holes, SMBHs, at the centers of galaxies. These black holes are thought to play a dominant role in regulating the growth of galaxies, with the energy produced by their accretion disks and jets driving the galactic winds. The relationship between SMBHs and their host galaxies is complex and still not fully understood, but it is clear that galactic winds play a vital role in this interplay. By studying how feedback from SMBHs influences galactic winds, scientists can gain a better understanding of how galaxies and black holes evolve together, shaping the large-scale structures of the universe. An important aspect of galactic wind research is the connection between the processes happening within individual galaxies and the broader cosmic landscape. As galactic winds expel gas and dust into the intergalactic medium, they contribute to the enrichment of the universe. This material, which was once a part of galaxies, is then spread across vast distances, providing the building blocks for new galaxies, stars, and even life itself. In a sense, the material that is expelled by galactic winds becomes a cosmic resource, traveling far beyond its galaxy of origin to influence the formation of new structures throughout the universe. This process is thought to be crucial for understanding the distribution of elements in the cosmos, from the lightest elements like hydrogen and helium to the heavier elements created in supernovae and other stellar processes. The fate of the gas and dust expelled by galactic winds is also a key factor in the evolution of the intergalactic medium, IGM, the vast, mostly empty space between galaxies. The IGM is thought to contain much of the gas that will eventually form new galaxies, stars, and other structures in the universe. By studying the interaction between galactic winds and the IGM, scientists can gain insight into the processes that govern galaxy formation on a cosmic scale. The exchange of material between galaxies and the IGM is a key driver of the large-scale structure of the universe, and understanding it is crucial for developing a comprehensive theory of cosmic evolution. The concept of galactic recycling, is also central to the study of galactic winds. This term refers to the ongoing process in which gas and dust are expelled by galactic winds and later reabsorbed by other galaxies or regions of the same galaxy. This cyclical process of expulsion and reabsorption plays a significant role in regulating the amount of gas available for star formation, the evolution of galaxies, and the enrichment of the intergalactic medium. Essentially, galactic winds are a form of cosmic recycling, helping to redistribute material throughout the universe and contributing to the creation of new stars, galaxies, and even life. Another emerging field in galactic wind research is the study of starburst galaxies undergoing intense episodes of star formation. These galaxies are often marked by exceptionally powerful galactic winds, driven by the large number of supernovae and the energetic activity from their central AGN. The winds from starburst galaxies can carry large amounts of gas and dust, influencing the evolution of both the host galaxy and its surroundings. Starburst galaxies are particularly important for understanding the role of galactic winds in triggering or suppressing star formation, as their winds can either drive gas away from the galaxy or compress it, leading to new waves of star formation. Studying these galaxies offers valuable insight into the complex interactions between star formation, galactic winds, and the overall evolution of galaxies. Finally, the discovery of galactic winds in distant galaxies has profound implications for our understanding of the universe's history and future. Observing these winds in galaxies at various stages of their evolution allows astronomers to trace the evolution of gas, dust, and stars across cosmic time. By studying how galactic winds have shaped the evolution of galaxies, scientists can piece together the larger story of how galaxies, stars, and the universe itself have evolved over billions of years. In this way, galactic winds offer a direct window into the past, revealing how the universe has developed and changed throughout its history. The study of galactic winds is a rapidly evolving field that promises to reshape our understanding of galaxy formation, evolution, and the large-scale structure of the universe. From the role of supernovae and active galactic nuclei to the interaction between galaxies and the intergalactic medium, galactic winds play a vital role in shaping the cosmos. As our observational tools and computational models continue to advance, we will be able to explore these phenomena in greater detail, uncovering new insights into the forces that drive the universe's evolution. With each new discovery, we move closer to unraveling the mysteries of galactic winds and their profound impact on the cosmos. As we continue to explore the effects and significance of galactic winds, it's important to consider how their study is not just about understanding individual galaxies, but also how it ties into broader questions about the universe's evolution. The concept of galactic winds intersects with fundamental questions in astrophysics about the fate of galaxies, star formation rates, and even the creation of new structures in the cosmos. By observing the winds that flow from galaxies, we get a unique glimpse into the complex and dynamic processes that govern the birth and death of stars, the interaction between galaxies, and the evolution of the universe itself. One area of particular interest is the role of galactic winds in regulating the balance between star formation and stellar death within a galaxy. It is widely accepted that the material in a galaxy, the gas and dust, plays a key role in the formation of new stars. However, once stars are formed, they also generate energy, radiation, and winds of their own, which can ultimately expel some of the material back into space. This interaction between star formation and the winds generated by these stars creates a kind of cosmic equilibrium, where the rate at which stars form can be balanced by the rate at which gas is lost from the galaxy. Galactic winds, particularly those driven by supernovae and the powerful activity of AGNs, act as a feedback mechanism, regulating the star formation process and the long-term growth of galaxies. Moreover, it's important to note that galactic winds aren't a uniform process across all types of galaxies. Different galaxies, depending on their size, structure, and composition, exhibit different wind dynamics. For example, a spiral galaxy like the Milky Way will likely produce galactic winds that behave differently than those in an elliptical galaxy or a dwarf galaxy. In large spiral galaxies, the winds may be channeled along the galaxy's spiral arms, while in elliptical galaxies, the winds might be more diffuse and slower moving. This variability underscores the complexity of galactic wind dynamics and highlights the need for careful study of each type of galaxy and its unique characteristics. To further complicate matters, the environmental conditions in which a galaxy resides also play a significant role in how its winds behave. For instance, galaxies in dense clusters, where galaxies are in close proximity to each other, might experience different interactions with the intergalactic medium, IGM, than isolated galaxies. The pressure from the surrounding IGM can either enhance or suppress the strength of the galactic wind. In some cases, galaxies that are part of a larger cluster may experience gas stripping, where their gas is removed by the intracluster medium, effectively depriving the galaxy of the raw materials needed for new star formation. Understanding these interactions is key to developing a holistic model of galactic wind behavior, as it highlights how local environments can influence the larger-scale dynamics of galaxies. The influence of galactic winds also extends beyond the individual galaxy and into the realm of galaxy clusters. Galaxy clusters, which are large collections of galaxies bound together by gravity, contain hot, diffuse gas known as the intracluster medium, ICM. The pressure from this gas can influence the formation and behavior of galactic winds. For example, as galaxies within a cluster expel gas and dust through their winds, they contribute to the enrichment of the intracluster medium, further fueling the cluster's overall evolution. In some cases, this process can lead to the formation of cool cores in galaxy clusters, where gas in the center of the cluster is heated by the energy from galactic winds, creating a complex feedback loop that affects star formation and the behavior of the cluster as a whole. At the most extreme scale, the role of galactic winds in shaping the evolution of large cosmic structures cannot be overstated. Galaxies themselves are not isolated entities. They are part of a larger cosmic web that stretches across the universe. This web consists of vast interconnected structures, such as galaxy clusters, superclusters, and filaments of dark matter, that form the scaffolding of the universe. Galactic winds, by pushing gas and dust out into the intergalactic medium, play a crucial role in the distribution of material across these vast cosmic structures. This material, which is expelled by galaxies, is eventually spread across the intergalactic voids, contributing to the enrichment of the universe with heavier elements. The concept of galactic winds ties directly into the study of large-scale cosmic evolution. The interaction between galaxies and the intergalactic medium, driven in part by these winds, contributes to the ongoing cycle of matter and energy that shapes the structure of the universe. For example, the release of gas from galaxies through their winds helps to enrich the universe with heavy elements, which are essential for the formation of planets and life. Without the redistribution of gas and dust by galactic winds, the universe would have a very different chemical composition, with fewer of the elements necessary for the formation of planets, stars, and other cosmic objects. In addition to the impact on galactic evolution, the study of galactic winds also offers important insights into the behavior of black holes, particularly supermassive black holes, SMBHs, found at the centers of many galaxies. These black holes are thought to play a crucial role in regulating the growth of galaxies, as their immense gravitational pull can influence the surrounding gas and trigger the formation of galactic winds. The energy generated by the accretion disk around a supermassive black hole can drive powerful jets of material into space, which can, in turn, trigger the galactic winds we observe. This interplay between SMBHs, galactic winds, and star formation is one of the most fascinating and still largely unexplored aspects of modern astrophysics. As we move forward in our study of galactic winds, we also begin to look more closely at the cosmic timeline. Observing galactic winds in distant galaxies provides a way to look back in time, as the light from these galaxies takes billions of years to reach us. By studying the winds in these far-off galaxies, we can better understand how the processes that drive galactic evolution, such as supernovae, AGNs, and feedback mechanisms, have shaped the universe throughout its history. This allows us to trace the development of galaxies and cosmic structures across cosmic time, helping us piece together the broader story of the universe's formation and evolution. Finally, the significance of galactic winds in shaping the future of the universe cannot be underestimated. As the universe continues to expand and evolve, galactic winds will continue to play a key role in regulating star formation, the growth of galaxies, and the distribution of material across the cosmos. The winds may continue to shape the fate of galaxies for billions of years to come, contributing to the overall cosmic cycle of birth, death, and rebirth. The study of galactic winds provides an unparalleled opportunity to explore the fundamental processes that shape the universe. From the behavior of supernovae and active galactic nuclei to the impact on star formation, galactic evolution, and the intergalactic medium, galactic winds offer critical insights into the workings of the cosmos. As our tools and observational capabilities continue to improve, we will gain an increasingly sophisticated understanding of how these winds shape the galaxies, star systems, and large-scale structures that make up the universe. By understanding these dynamic and complex phenomena, we are unlocking the secrets of cosmic evolution and uncovering the forces that govern the universe on the grandest scale. As we continue our exploration of galactic winds, it's essential to discuss the various methods scientists use to observe and study these enigmatic phenomena. While galactic winds can't be directly seen with the naked eye, astronomers have developed an arsenal of sophisticated tools to probe the invisible forces at play. The detection of galactic winds typically involves studying the emission lines in the light coming from galaxies, which are altered by the presence of high-energy particles moving through space. These emissions, often detected by space-based telescopes, allow scientists to infer the velocity, composition, and energy of the winds. Spectroscopy is one of the most powerful techniques for studying galactic winds. By dispersing light into its component wavelengths, scientists can analyze the shifts in the light spectrum caused by the motion of gas and particles. The Doppler shift is key here. As the material in a galactic wind moves away from or toward Earth, the light shifts to longer or shorter wavelengths. This shift reveals information about the speed and direction of the wind, giving researchers a detailed picture of its behavior. Different elements within the wind, such as hydrogen, oxygen, and metals, emit light at characteristic wavelengths, which helps scientists understand the composition of the gas and the physical conditions within the wind. Moreover, the study of galactic winds often goes hand in hand with observations of supernovae and active galactic nuclei, AGNs. Supernovae, the explosive deaths of massive stars, are one of the key sources of energy that drive galactic winds. When a supernova occurs, it releases an enormous amount of energy, expelling gas and dust into the surrounding space. This material can be detected through the observation of shock waves in the surrounding gas, as well as the light emitted during the explosion. Similarly, AGNs, which are powered by supermassive black holes at the centers of galaxies, produce intense radiation and jets that can drive powerful outflows of material. By studying the light and radiation from AGNs, astronomers can learn more about the role these objects play in the generation of galactic winds. Another fascinating aspect of galactic wind studies is their connection to the concept of feedback in galaxy evolution. Feedback refers to the idea that the energy and material expelled by stars, supernovae, and AGNs affect the surrounding environment, influencing the rate of star formation and the overall evolution of the galaxy. In this context, galactic winds are seen as a form of negative feedback, in which the energy and material ejected from the galaxy reduce the amount of gas available for new star formation. This interplay between star formation and galactic winds is one of the key mechanisms that regulate the growth of galaxies over time. In addition to their role in galaxy evolution, galactic winds are crucial for understanding the large-scale structure of the universe. As material is expelled from galaxies and carried into the intergalactic medium, it enriches the overall composition of the universe. This process, called metal enrichment, is fundamental to the creation of elements like carbon, oxygen, and iron, which are essential for the formation of planets and life as we know it. The study of galactic winds provides valuable insights into how galaxies contribute to the chemical evolution of the universe, helping to answer questions about the origins of the elements that make up everything around us. One of the most exciting areas of research in this field is the role of galactic winds in the context of galaxy mergers. When two galaxies collide, their gas and dust can be funneled into a central region, triggering an intense burst of star formation. However, this process is often followed by the ejection of large amounts of gas through the resulting galactic winds. The interaction between these winds and the intergalactic medium can have profound effects on the evolution of the merged galaxies, potentially slowing down or even halting star formation in the long term. By studying galactic winds in the aftermath of galaxy mergers, scientists are learning more about the processes that govern galaxy evolution and how galaxies form and grow over time. Another emerging avenue of study is the connection between galactic winds and the formation of cosmic voids. Cosmic voids are vast, empty regions of space that exist between the large-scale structures of the universe, such as galaxy clusters and superclusters. These voids are thought to play a critical role in the distribution of galaxies and the overall evolution of the universe. Some theories suggest that galactic winds, by expelling gas and dust into the intergalactic medium, contribute to the creation and expansion of these voids. By studying the interaction between galactic winds and cosmic voids, researchers hope to uncover more about the underlying forces that shape the large-scale structure of the cosmos. As our observational technology advances, we are also gaining new insights into the role of galactic winds in the early universe. Observations of distant galaxies, whose light has taken billions of years to reach us, provide a snapshot of the universe at a time when it was still young. By studying the galactic winds in these ancient galaxies, scientists can better understand the conditions that prevailed during the formation of the first galaxies and the early stages of cosmic evolution. These observations may hold the key to understanding how galaxies, stars, and even the first elements were formed in the aftermath of the Big Bang. In terms of technological advancements, the development of more powerful space telescopes is significantly enhancing our ability to study galactic winds in unprecedented detail. Instruments like the James Webb Space Telescope, JWST, are designed to observe distant galaxies and their winds in the infrared spectrum, allowing us to peer through cosmic dust and gas to see the underlying processes. These new capabilities will undoubtedly revolutionize our understanding of galactic winds and their role in shaping the universe. The study of galactic winds is also linked to the broader field of cosmology, as these outflows provide critical clues about the fundamental nature of matter, energy, and the forces that govern the universe. For example, the detection of high-energy particles in galactic winds can help to answer questions about the nature of dark matter and dark energy, the mysterious substances that make up most of the universe. Understanding the dynamics of galactic winds can thus shed light on some of the deepest mysteries in physics and cosmology, providing a more complete picture of the universe's evolution. In the context of galactic wind research, it is also important to highlight the role of simulations and computational models. Given the complexity of galactic dynamics, it is often difficult to make direct observations of all the relevant factors influencing wind behavior. To overcome this, scientists use simulations to model the physical processes involved in galactic wind formation. These simulations take into account the interaction of gas, dust, radiation, and gravitational forces, providing a theoretical framework that complements observational data. As computational power increases, these simulations become more sophisticated, allowing scientists to test different hypotheses and refine our understanding of how galactic winds operate across various scales. In summary, the study of galactic winds offers us an unparalleled view into the complex processes that govern the life cycle of galaxies and the universe at large. From their role in regulating star formation and shaping galaxy evolution to their impact on the distribution of gas and dust across the cosmos, galactic winds are at the heart of some of the most fundamental questions in astrophysics. As our observational tools and theoretical models continue to evolve, we can expect to gain even deeper insights into these cosmic phenomena, further unraveling the mysteries of the universe. Galaxies, through their winds, offer us a window into the processes that have shaped the universe from its earliest moments and continue to influence its evolution today. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.